There is a number in modern physics that almost nobody ever hears, and it is far smaller than you would guess. Less than 1%. That is how much of a proton's mass is accounted for by the mass of the particles inside it. 2 up quarks and 1 down quark, added together, come to about 9 units. The proton they sit inside comes to 938, and because protons and neutrons carry essentially all the mass of every atom, that missing 99% is not some obscure detail of particle physics. It is the weight of your own body. It is the heaviness of every object you have ever lifted. Whatever mass actually is, it is not the amount of stuff in a thing, and by the end of tonight you will know exactly what it is instead. Before we begin, if you enjoy having something this ordinary taken apart slowly, a quick like or subscribe really helps the channel grow. It costs you nothing, and it means the world to me. Now, let's begin. There is a sensation so ordinary that almost nobody has ever stopped to examine it. You reach out, you close your fingers around something, and you lift. A mug of tea, a hardback book, a stone picked up off a path because it had a nice shape to it. In the instant your hand takes the load, you learn something about that object, without measuring anything, without thinking about it, without any conscious effort at all. You learn how heavy it is, and along with that you feel you have learnt something about what it is made of. Pick up a bowling ball, and the message is unmistakable. It resists. It takes effort to lift, effort to move, effort to stop once it is rolling. Pick up a tennis ball, and there is almost nothing there. You can toss it from hand to hand, without bracing yourself, without adjusting your posture, without any of the small anticipatory tensing your body does automatically when it expects a load. The difference between those two objects is mass, and your body reads it instantly, with no instruments and no training. If someone asked you what mass actually is, you would probably give an answer that sounds entirely reasonable, and you would be in excellent company, because it is the same answer nearly everyone gives. Mass is the amount of matter in something. Mass is how much stuff is in there. The bowling ball has more stuff packed inside it than the tennis ball, so it weighs more. That is the intuitive answer. It is the answer most of us were given at school, and in everyday life, it works beautifully. A brick outweighs a feather, a car outweighs a bicycle, a planet outweighs a pebble. More stuff, more mass. Simple, useful, and apparently obvious. This idea feels so natural that most people never question it once in their entire lives. Mass is substance. Mass is material. Mass is the physical stuff filling an object and giving it weight. And if you could somehow count all the little pieces inside and add up their heaviness, you would arrive at the number a scale gives you. For centuries, this intuition did not merely feel right, it worked. It guided engineers building bridges and ships and cathedral domes. It let astronomers calculate the paths of planets they would never visit. It gave Isaac Newton everything he needed to write down laws of motion that are still taught, still used, and still correct within their range. When Newton wrote that force equals mass times acceleration, he treated mass as a straightforward quantity. It was a number you assigned to an object, representing how much matter that object contained, and how strongly it resisted being pushed. The more mass something had, the harder it was to accelerate. The more mass something had, the more strongly it pulled on other massive things through gravity. Mass sat at the foundation of physics as the most basic property matter could have. It seemed like the simplest concept in the whole of science, and for a long time, nobody had any reason to look underneath it. But something happened over the last 120 years, and it happened quietly, in laboratories and on chalkboards, and eventually inside supercomputers. Physicists went looking for the stuff that mass is made of, and they did not find it. Not because they failed, because it is not there. I want to be precise about what that means, because it is easy to hear it as mysticism, and it is not mysticism. It is the opposite of mysticism. It is arithmetic. When physicists finally got far enough down into matter to weigh its smallest known components, they added those weights up, compared them to the weight of the object those components make, and the numbers did not match. They did not match by a little. They missed by more than 99%. And the gap has since been explained, calculated from first principles, and confirmed against experiment to a precision that leaves very little room for argument. More than 99% of the mass in your body is not substance. More than 99% of the mass of this planet is not substance. The weight you felt a moment ago when you imagined lifting a stone was almost entirely something else. Something that has no material existence at all in the way you have always assumed material things exist. And by the end of tonight, you are going to know exactly what it is, where it comes from, and how anybody could possibly have found out. But we have to get there in the right order, because the answer only means something if you first understand why the obvious answer fails. And the obvious answer fails in a very specific place, at a very specific depth, and it fails after holding up perfectly at every level above it. So let us do what physics did. Let us go inward, not outward into space, not forward into deep time, but inward into matter itself, layer by layer, and at every layer we will ask the same simple question: where does the mass come from? You will find, for a surprisingly long time, that the question has a very satisfying answer. Every time you break something open, the mass of the whole turns out to be the mass of the pieces inside. That pattern holds through chemistry. It holds through the discovery of the atom. It holds through the discovery that atoms have parts. It holds all the way down to particles so small that 100,000 of them, laid side by side, would barely span a single atom. And then it stops holding, completely, all at once. Start where you are. The world around you is made of materials, and materials are the level at which human beings have always dealt with matter. Wood, iron, water, stone, glass, plastic, bone. These things behave differently from one another, in ways your hands know intimately. Some are hard, and some yield. Some are cold to the touch, and some are not. Some conduct electricity, and some refuse to. Some float, and some sink. For most of human history, that was the whole taxonomy of matter, the practical knowledge of a species that built things. But every one of those materials, without exception, is made from the same limited set of ingredients. They are all combinations of chemical elements. You have probably seen the periodic table on a classroom wall, that lopsided arrangement of boxes that manages to look both arbitrary and inevitable. It lists every element known, from hydrogen, the lightest, up through the artificial heavyweights that exist only for fractions of a second inside accelerators. About 92 of them occur naturally on Earth. 92. Everything you have ever seen, touched, eaten, breathed, or drunk is made from combinations of those 92 things. Water is hydrogen and oxygen. Table salt is sodium and chlorine. The steel in a bridge is mostly iron, with a little carbon stirred in. The air moving in and out of you right now is mostly nitrogen and oxygen, with traces of argon and carbon dioxide along for the ride. You are mostly oxygen, carbon, hydrogen, and nitrogen, arranged with extraordinary care. And here is where the trail begins, because the moment you know that everything is made of a small number of elements, the obvious next question arrives on its own. What are the elements made of? Somebody asked that question about 2,400 years ago, and the answer they gave was so far ahead of its time that it took 2,000 years for anyone to prove it. It was also, in a way nobody could have anticipated, wrong about the one thing we are here to talk about. The man who asked the question first, as far as we know, was a Greek philosopher named Democritus, working roughly 2,400 years ago with no microscope, no laboratory, and no experimental tools of any kind. His method was pure reasoning, and his reasoning went like this. Take a piece of matter, cut it in half again. Keep going. Either you can do this forever, or at some point you reach a piece so small that it cannot be divided any further. Democritus decided it must be the second one, and he gave those final indivisible pieces a name. He called them atomos, which means uncuttable. His picture was remarkably close to modern. Everything in the world was built from these tiny, indivisible particles. Different substances behaved differently because their atoms had different shapes and fitted together in different arrangements. Iron atoms hooked into one another and made something hard. Water atoms were smooth and rolled over each other and made something that flowed. He had no way to test any of it, but the structure of the idea was right, and it was arrived at by sitting still and thinking carefully. Aristotle disagreed, and Aristotle's disagreement mattered a great deal more than Democritus's argument, because Aristotle became the most influential thinker in the Western world for the next 2 millennia. Aristotle believed matter was continuous. You could always divide it further. There was no smallest piece, no flaw, no end to the halving. And because his authority was so enormous, the idea of atoms was pushed to the margins for nearly 2,000 years, kept alive as an interesting speculation and nothing more. Atoms came back in the early 1800s, and they came back through weighing. A British chemist named John Dalton noticed something about chemical reactions that nobody had properly explained. When elements combined into compounds, they always combined in fixed ratios by mass. Not approximately, exactly. 8 grams of oxygen always joined with 1 gram of hydrogen to make water. Never 7, never 9. Every reaction Dalton studied showed the same rigid arithmetic, and the arithmetic only made sense if matter came in discrete lumps with specific, definite masses. If a water molecule always held 2 hydrogen atoms and 1 oxygen atom, and if an oxygen atom was always 16 times heavier than a hydrogen atom, then the ratio of masses could not be anything other than 8:1. The fixed ratios were the fingerprints of atoms. Notice what Dalton's evidence actually was. It was mass. Atoms became scientifically respectable because of how much they weighed relative to one another. And Dalton, quite reasonably, assumed he had reached the bottom. Atoms were the fundamental building blocks, solid and indivisible, the smallest things that exist. In Dalton's picture, the mass of an object was simply the total mass of all its atoms added together, and atoms had mass because they were stuff. They were the stuff. There was nothing underneath to explain. Then, in 1897, in a laboratory in Cambridge, that floor gave way. J.J. Thomson was working at the Cavendish laboratory with cathode rays, the streams of something that appear inside a glass tube when you run an electric current through it. By measuring carefully how those rays bent in electric and magnetic fields, Thomson worked out that whatever the rays were made of, it was far lighter than any atom, roughly 1,800 times lighter than a hydrogen atom, the lightest element there is. He had found the electron, a particle smaller than an atom, and in finding it, he had proved that atoms are not indivisible after all. They have insides. They have parts. This was not a small correction. If atoms have parts, then the mass of an atom is not fundamental. It is the combined mass of those parts, which means the question has moved rather than been answered. What else is in there? Thomson's own guess was that an atom was a diffuse ball of positive charge with electrons stuck in it, like currants in a pudding. It was a sensible proposal given what he knew, and it lasted about 14 years. In 1911, in Manchester, Ernest Rutherford and his colleagues put it to the test. Imagine the room. It is dark, deliberately so, because the only way to see what is happening is to watch for individual faint flashes of light. There is a small source of radium sealed in lead, firing alpha particles, which are helium nuclei, in a narrow beam. In the path of that beam, there is a sheet of gold foil, so thin it is almost transparent, hammered down to a few thousand atoms in thickness. On the far side, mounted on a swivel, there is a screen coated in zinc sulfide that gives off a tiny green scintillation each time a single alpha particle strikes it, and behind the screen there is a microscope, and pressed to the microscope there is a human eye. Somebody has been sitting in the dark for a long time already, letting their vision adapt, counting flashes one at a time, and calling the numbers out. Most of the flashes land exactly where they should, straight ahead, the alpha particles sailing through the foil as though it were not there. That is expected. Then the screen is swung around to look for particles that came back. Not deflected slightly, came back, toward the source. And every so often, in the dark, there is a flash. Rutherford said later that it was as if you had fired a 15-inch artillery shell at a sheet of tissue paper and it had bounced back and hit you. Roughly 1 alpha particle in 8,000 did it. But 1 is enough, because nothing in Thomson's diffuse pudding could turn a fast helium nucleus around. Only something tiny, hard, dense, and positively charged could do that. And the arithmetic said that something had to be carrying essentially all of the atom's mass in a region thousands of times smaller than the atom itself. That was the nucleus, and the picture of the atom that came out of it is one of the strangest results in physics, precisely because it is so familiar that we have stopped noticing how strange it is. The atom is almost entirely empty space. If you scaled a single atom up to the size of a football stadium, the nucleus would be a small marble sitting at the center of the pitch, and everything else, all the way out to the seats in the top tier, would be nothing but electron cloud. Yet that marble carries more than 99.9% of the mass. Sit with that for a moment, because it is the first hint that mass does not behave the way you expect. Mass is not spread evenly through matter. It is concentrated, hoarded, gathered into an almost inconceivably small volume, and the enormous airy structure around it contributes essentially nothing to what your scale reads. Over the following decades, the nucleus was opened too, and found to have parts of its own. There are 2 kinds of particle in there: protons, which carry positive electric charge, and neutrons, which carry no charge at all. They have almost the same mass as each other, and each of them is about 1,836 times heavier than an electron. How many protons a nucleus has decides which element the atom is. 1 proton, and it is hydrogen. 2, and it is helium. 6, and it is carbon, the element most of your dry mass is built from. 92, and it is uranium. The neutrons add mass and help hold the whole arrangement together against the fierce electrical repulsion of all those positive charges crowded into one place. So by the middle of the 20th century, the ledger looked complete, just pushed a few levels deeper than Dalton ever imagined. The mass of an object is the mass of its atoms. The mass of an atom is very nearly the mass of its nucleus. The mass of a nucleus is the combined mass of its protons and neutrons. And protons and neutrons are the fundamental things. They are the stuff. They are where mass lives. Every step of that chain had held. 4 times in a row, when physics broke something open, the mass of the whole turned out to be the mass of the pieces. There was no reason on earth to expect the 5th step to behave any differently. It did not behave differently. It behaved catastrophically differently. The trouble started with a bookkeeping problem. Through the 1950s and into the 1960s, particle accelerators kept producing new particles nobody had ordered, not 2 or 3, dozens. They had different charges, different lifetimes, different decay habits, and no obvious organizing principle, and physicists began referring to the situation, without affection, as the particle zoo. One of them reportedly said that if he had known there would be this many, he would have gone into botany. 2 people found the pattern independently. In 1964, Murray Gell-Mann at Caltech and George Zweig, then at CERN, both noticed that the whole unruly collection fell into neat geometric families if you assumed each of those particles was not fundamental at all, but built out of a small number of smaller components combining in particular ways. Gell-Mann took the name for those components from a line in James Joyce's Finnegan's Wake, 3 quarks for muster mark, which appealed to him because he had already decided there were 3 of them in a proton. A proton, in this scheme, contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. The quarks are bound to one another by particles called gluons, which carry the strong nuclear force, the most powerful force in nature. Now, a mathematical pattern is not a discovery. Plenty of elegant schemes in the history of physics have turned out to describe nothing. What turned quarks from a filing system into physical objects was a set of experiments at Stanford, at the linear accelerator known as SLAC, running from about 1967 onward. The method was Rutherford's method, updated by half a century. Fire something very small and very fast at a proton and see how it comes off. The projectiles this time were electrons at high energy, aimed at hydrogen targets, which is to say, aimed at bare protons. If a proton were a smooth, uniform little blob of matter, the electrons would graze off it gently, deflecting through small angles, like marbles, rolling across a pillow. That is what most physicists expected. That is not what happened. Every so often, an electron came off at a sharp, violent angle, and some of them came very nearly straight back. The scattering pattern looked almost exactly like Rutherford's gold foil, 60 years earlier, in a different country, at a different scale. Something small and hard and point-like was sitting inside the proton. Richard Feynman, visiting SLAC while this was going on, understood immediately what the data was saying and pointedly refused to say what the hard objects were. He called them partons, meaning simply parts, and left it there. Meanwhile, the theorists had quarks. It took a few years for everyone to agree, but by the mid-1970s, the two descriptions had converged because they were descriptions of the same thing approached from opposite ends. Feynman's partons and Gell-Mann's quarks were one and the same. The Jerome Friedman, Henry Kendall, and Richard Taylor received the Nobel Prize for that scattering work in 1990. So the proton was not fundamental either. The ledger extended one more line. The mass of an object is the mass of its atoms. The mass of an atom is the mass of its nucleus. The mass of a nucleus is the mass of its protons and neutrons, and the mass of a proton is the mass of its quarks. That last line is false, not slightly false, not false in a way that needs a correction term, false by 2 orders of magnitude. Here are the numbers, and I want to go slowly through them, because everything else in this video grows out of this one comparison. The mass of a proton is measured with almost absurd precision. In the units particle physicists use, it is about 938.27 mega-electron volts divided by the speed of light squared. That looks like a strange way to state a mass, and there is a reason for it that we will come to. But for now, treat it as a number on a scale. 938. In kilograms, it is 1.67 times 10 to the minus 27, and we know it to roughly 10 decimal places, which is the equivalent of measuring the distance from London to New York to within a couple of millimeters. A word about that unit, because it matters later. The mega-electron volt is a unit of energy, not of mass, and physicists use it for mass by dividing it by the speed of light squared. 1 mega-electron volt divided by the speed of light squared works out to about 1.78 times 10 to the minus 30 kilograms. The fact that particle physicists find it natural to quote masses in units of energy is not laziness or jargon. It is the first quiet admission in this whole subject that the two things are the same thing, and they were writing it that way for decades before anyone worked out how thoroughly true it was. Now weigh the contents. An up quark has a mass of about 2.2 of those same units. A down quark has a mass of about 4.7. For comparison, the electron comes in at 0.511, and the third lightest quark, the strange quark, sits far above both at around 93. A proton contains 2 up quarks and 1 down quark. 2 times 2.2 is 4.4. Add 4.7 for the down quark. The total mass of the 3 quarks inside a proton comes to roughly 9. 9 inside 938. That is less than 1%. Not 90%, with a bit missing. Not half, not even 10%. Less than 1% of a proton's mass is accounted for by the mass of the things inside it. There is an honest complication in those quark numbers that I should mention rather than hide, because it makes the conclusion stronger rather than weaker. Quark masses cannot be measured the way the proton's mass can, by putting one on a scale, because you can never get hold of a single quark. They have to be inferred, and their quoted values depend on a technical convention about the energy scale at which you define them. The numbers I just gave are the standard ones at a scale of 2 giga-electron-volts, and they carry uncertainties of tens of percent, which is embarrassing next to the proton's 10 decimal places. But nothing about that changes the verdict. You can push the conventions around as much as you like, and the quark contribution stays down in the neighborhood of 1%. There is no choice of scheme that rescues the old picture. Let that sit for a moment, because it is worth understanding what has just happened. For 3 centuries, through 4 successive layers of matter, the rule held without exception. The mass of the whole is the mass of the parts. It held for objects made of atoms. It held for atoms made of nuclei and electrons. It held for nuclei made of protons and neutrons. Then physics arrived at the deepest layer it can currently reach, opened it, weighed the contents, and the contents came to under 1% of the container. And this is not an obscure fact about an exotic particle. Protons and neutrons carry more than 99.9% of the mass of every atom, because electrons are so light as to be almost negligible. Atoms carry essentially all the mass of ordinary matter. So the missing 99% is not hiding in some corner of particle physics. It is the mass of your hand. It is the mass of the chair holding you up, the floor holding the chair, the planet holding the floor. It is the number your bathroom scale gives you. If you weigh 70 kilograms, then something in the region of 69 of those kilograms has, at this point in the story, no explanation whatsoever. The stuff you are made of does not weigh enough to be you. I want to be careful here, because there is a lazy version of this fact that circulates widely, and it is wrong. The lazy version says mass is an illusion. Matter is not real. None of it is really there. That is not what the arithmetic says. The proton's mass is real. You can measure it, you can weigh it, you can feel it. It bends space-time, it resists being pushed, it does absolutely everything mass is supposed to do. Nothing about it is fake. What the arithmetic says is that mass is not made of what we assumed it was made of. And that is a far more interesting statement than the mystical one, because it can be checked. So where is it? Where does the other 99% come from? I am not going to answer that yet, and I want to tell you why. The answer involves 2 completely separate mechanisms that operate on 2 different kinds of particle, and almost every popular account of this subject collapses them into one and gets the whole thing backwards as a result. If you have heard of one of these mechanisms, you have heard of the wrong one for this purpose, or at least the smaller one. To see the real answer clearly, you need one idea in place first, and it is an idea that sounds like a technicality and turns out to be the most important shift in how physicists picture reality. The idea is that particles are not the fundamental things in the universe. They never were. You have a picture in your head of what a particle is, and you did not choose it. It was installed early, probably by a textbook diagram, and it looks something like a very small ball. An electron is a tiny sphere orbiting a nucleus. A photon is a little packet of light traveling in a straight line. A quark is a smaller ball inside a slightly larger ball. Particles are objects. They sit somewhere. They move from place to place. They have surfaces, or at least edges. That picture is not merely simplified. In the framework physicists actually use to describe nature, it has the whole structure backwards. Particles are not the fundamental furniture of reality. Fields are. And a particle is what you get when a field is disturbed in a particular way. This is quantum field theory, and it is the most precisely tested description of the physical world that human beings have ever produced. It came together over about 20 years. Paul Dirac took the first serious step in the late 1920s, when he combined quantum mechanics with Einstein's special relativity, and found that the equation he had written down insisted on the existence of a particle identical to the electron, but with the opposite charge. Nobody had ever seen such a thing. It was found 4 years later. Antimatter was not discovered, and then explained. It was predicted by an equation, and then found, which is the sort of thing that makes physicists trust their mathematics rather more than is entirely healthy. Then in the late 1940s, Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, working independently, and in Tomonaga's case, in a Japan still in ruins from the war, built the first fully successful quantum field theory. It described how electrons and light interact, and it is called quantum electrodynamics. Its predictions match experiment to more than 10 decimal places. To put that in perspective, the theory's calculation of the electron's magnetic behavior agrees with the measured value at a level of precision comparable to knowing the distance from here to the moon to within the width of a human hair. It remains one of the most accurate predictions in the history of science, and it is the reason nobody was willing to throw the framework away later, even when it seemed to forbid something that obviously exists. So what is a field? A field is a quantity that has a value at every point in space. That is all. The temperature in a room is a field in this loose sense. Every point in the room has a temperature, and the collection of all those values is the temperature field. A quantum field is the same idea taken seriously and taken all the way down. There is an electron field. It exists everywhere, in this room, inside your body, in the emptiest volume between galaxies. There is an electromagnetic field, likewise everywhere. There is an up quark field, a down quark field, a gluon field, a neutrino field, and one for every other elementary particle in the catalogue. And what we call a particle is a localized vibration in one of those fields, an excitation, a ripple. Picture a lake at dawn with no wind. The surface is perfectly flat, undisturbed, and if you did not know better, you would say nothing is happening there. That is a quantum field in its lowest energy state, what physicists call the vacuum. Now drop a pebble. A ripple spreads out. It has a location. It carries energy. It moves. It can meet other ripples and interfere with them, add to them, cancel them. And crucially, the ripple is not a separate object from the lake. There is no thing in the water. There is water, doing something. That is what an electron is. Not a small ball moving through space, but the electron field doing something. Here, rather than there. Drop 2 pebbles, and you have 2 ripples that can interact and combine, and, under the right conditions, annihilate. Particles are created and destroyed all the time in this picture, and that stops being mysterious once you stop thinking of them as objects. Waves appear and disappear on a lake without anything being manufactured or destroyed. The lake is always there. The ripples come and go. This also explains something that used to trouble people badly about Dirac's antimatter. If an electron and a positron meet and vanish in a flash of light, where did the electron go? In the old picture, that question has no comfortable answer, because a thing has ceased to exist. In the field picture, there is nothing to explain. Two disturbances in two fields cancelled one another, and the energy they carried moved into the electromagnetic field instead, where it now appears as photons. Nothing was destroyed, because nothing was ever a thing. The books balance, because energy is what is being tracked, not objects. Notice also what this does to the idea of empty space. In the old picture, empty means nothing there. In the field picture, empty means every field in existence is sitting at its lowest available value at that point, which is a positive statement about a place that is very full of something. All the fields are still present. They are just quiet. Keep hold of that, because in a moment, we are going to meet a field that is not quiet even at its quietest, and that single peculiarity is the reason anything in the universe has mass at all. Now hold on to why we came here. We are trying to find where more than 99% of the mass of ordinary matter comes from, and we have just changed the terms of the question. If particles are ripples in fields, then asking what a particle is made of is the wrong question, because it is not made of anything smaller. It is a state of something larger, and that reframing opens up a question you could not even have asked before. Some ripples are heavy, and some are not. A ripple in the electron field behaves like a particle with mass. It moves slower than light. It can be brought to rest. A ripple in the electromagnetic field, which is to say a photon, has no rest mass at all, travels at the speed of light, and can never be stopped or slowed. Both are excitations of a field. Both obey the same general framework. And yet one of them has mass, and the other does not. So there must be something about the fields themselves that makes the difference. That question has an answer, and the answer is one of the great results of 20th century physics. But before we get to it, there is a distinction to make, and if you keep hold of this distinction, you will never be confused by a popular science article about mass again. Because there are two kinds of particle in the world, and they get their mass in two entirely different ways. The first kind are elementary particles. As far as anyone can tell, these have no internal structure. They are not made of anything smaller. They are the bottom of the chain, the ripples in the fundamental fields themselves. Quarks are elementary. Electrons are elementary. Photons are elementary. Neutrinos, those almost weightless particles passing through your body by the trillion every second without touching anything, are elementary. So are muons, tau particles, gluons, and the W and Z bosons that carry the weak nuclear force. All of them are catalogued in the standard model of particle physics, which is the most successful and most precisely tested theory science has. The second kind are composite particles. These are made of smaller particles bound together. A proton is composite, quarks and gluons. A neutron is composite. A nucleus is composite. An atom is composite. A molecule is composite. You are composite, built from layer upon layer of composites, all the way down. It is worth pausing on how short that first list is, because the tidiness of it is part of why physicists believe it. There are 6 kinds of quark, arranged in 3 pairs of increasing heaviness. There are 6 light particles called leptons, which include the electron and the 3 kinds of neutrino. There are the force carriers, the photon, the gluon, and the W and Z bosons. And there is one more field that does not carry a force, and is not a constituent of matter, which is the one we are about to meet. That is, the entire inventory of the fundamental world. Every object you have ever encountered, every star, every living thing, every thought you have ever had, is built from a list you could write on the back of a receipt. And here is the sentence that most popular accounts of mass never say out loud. The mass of an elementary particle comes from one mechanism. The mass of a composite particle comes from a completely different mechanism. Mixing those two up, or assuming that one explanation covers both, is the single most widespread error in the public understanding of this subject. The elementary story is the famous one. It involves a field that behaves unlike any other field in nature, that fills every cubic centimetre of the universe, including the space your body is currently occupying, and whose existence took nearly half a century to confirm. That story accounts for the electron's mass and the quark's mass, which is to say, it accounts for the 9, not the 938. We will take the famous story first, because you have to understand what it does explain before you can appreciate the size of what it leaves out. Every quantum field in nature has a lowest energy state, and in every case but one, that lowest state has a value of 0. Think about the electromagnetic field. Out in the emptiest volume you can imagine, far from any charge, any magnet, any star, the electromagnetic field is 0. There is no light, no electric pull, no magnetic push. The field is sitting at the bottom of its range, and the bottom of its range is nothing. If you want a photon, you have to put energy in and lift the field above 0. The same is true for the electron field, the quark fields, and every other field in the catalogue. Their resting value is nothing at all. There is one exception, and the exception is the reason you have mass. The Higgs field does not rest at 0. Its lowest energy state, the state it settles into when nothing is disturbing it and there is no energy to spare, is a state where the field has a constant non-zero value everywhere in space. Not because something is exciting it, not because energy is being pumped in from somewhere, left entirely alone, in the coldest and emptiest region of the universe. The Higgs field sits at a value of roughly 246 giga-electron volts and stays there. That is its floor. 0 would cost it more energy than 246 does. If that sounds like a technicality, it is not. It changes everything about what kind of universe this is. It helps to picture why 0 can cost more than something. For an ordinary field, the energy stored rises as you move away from 0, so the field slides back down to 0, the way a marble rolls to the bottom of a bowl. For the Higgs field, the shape of that energy landscape is different. It is not a bowl with its lowest point in the middle. It is more like a shallow dome, with a circular trough running around its base, so the point directly under the center is a hill rather than a valley, and the marble cannot stay there. It rolls off, in some direction, and comes to rest somewhere in the trough. 0 is not a resting place. It is a summit, and the field is not balanced on it, because nothing in the universe stays balanced on a summit for 14 billion years. The value it rolls to, 246 giga-electron volts, is one of the most consequential numbers in physics, and it is not a particle mass. It is the setting of a dial. Every elementary particle mass in the Standard Model is that one number multiplied by how strongly the particle in question couples to the field. Change the number, and every mass in the universe changes with it. Here is a way to feel the difference, and I want to flag in advance that the analogy is imperfect in an important way I will correct in a moment. Imagine walking across a room. The air is there, all around you, and you barely register it. Move slowly, and it offers almost no resistance at all. Now imagine walking through waist-deep water. Every step is work. The medium pushes back. You feel slower, heavier, more difficult to move, not because your body changed, but because the thing you are moving through interacts with you. The Higgs field does something loosely like that for elementary particles. Because its value is not 0 anywhere, particles that couple to it are permanently immersed in it. There is no region of space where the field is absent. There is nowhere to go to escape it. And for a particle that interacts with the Higgs field, that unavoidable, constant interaction produces the property we measure as mass. It produces resistance to acceleration. It produces inertia. Now the correction, because this is where nearly everyone goes wrong. The Higgs field is not friction. It does not slow particles down. It does not drain their energy. An electron traveling through the Higgs field does not gradually decelerate the way a ball rolling through mud does. nothing is being lost. What the interaction does is change the electron's fundamental relationship with spacetime. Without it, the equations of the Standard Model say the electron would be massless and would travel at the speed of light, permanently, with no possibility of ever being at rest, exactly like a photon. With the Higgs field present, the electron acquires rest mass. It drops below light speed. It becomes something that can sit still, which means it becomes something that can be captured into orbit around a nucleus, which means chemistry becomes possible, which means you become possible. That is the real function of the Higgs field. It is not a supplier of heaviness. It is the reason anything can hold still. The same applies to quarks. Without the Higgs field, up quarks and down quarks would be massless and would race around at light speed, and nothing could ever bind them into a stable object. With the field switched on, they acquire small but definite rest masses, about 2.2 units for the up quark and 4.7 for the down. Small numbers, real numbers, Higgs numbers. And those are precisely the 9 units we found inside the proton, which means the famous mechanism, the one everybody has heard of, is responsible for the 1%, not the 99. Different particles interact with the Higgs field at different strengths, and this is where the story becomes genuinely strange. The strength of the coupling decides how much mass the particle ends up with. An electron couples weakly and comes out at 0.511 mega-electron volts. A top quark couples enormously strongly and comes out at about 172 giga-electron volts, which makes it roughly 338,000 times heavier than the electron. Both are elementary. Neither has any internal structure. Neither is made of anything. The entire difference between the lightest charged particle in the Standard Model and the heaviest is how tightly each of them grips the same field. So why do they grip it differently? Nobody knows. That is not a rhetorical setup. It is the actual state of the subject. The numbers that describe those coupling strengths are called Yukawa couplings, and the Standard Model does not predict a single one of them. They are measured in experiments and then written into the equations by hand as inputs. There is no derivation. There is no principle that says the top quark should be 338,000 times heavier than the electron, rather than 9 times or 9 million times. The most successful theory in the history of science, which predicts the behavior of the electron to more than 10 decimal places, cannot tell you why the electron weighs what it weighs. If a pattern exists behind those numbers, finding it would be one of the largest results in modern physics. People have been looking for 50 years. There is one more thing the Higgs field does, and it is the part of this story that I find hardest to hold in my head, because it is not about particles at all. It is about a moment in time. The Higgs field has not always had a non-zero value. In the extremely early universe, when everything was unimaginably hot, the field sat at zero like every other field, and the consequence of that is difficult to overstate. Every elementary particle in existence was massless. All of them traveled at the speed of light. There were no atoms, because a massless electron cannot be captured into an orbit. There was no chemistry. There was no structure of any kind. There was radiation, and there were massless particles streaming through space at the only speed available to them, and nothing else. And then the universe cooled below a threshold, and the field changed. Hold that moment. The universe is younger than 100 billionth of a second. It is a uniform blaze at something like 1,000 trillion degrees, and it is expanding fast enough that its temperature is falling by the instant. Every particle in it is moving at the speed of light, because none of them is capable of anything else. There is no such thing as being still. There is no such thing as here rather than there, because nothing can stay anywhere. And filling all of it, at a value of exactly zero, is a field nobody will name for another 14 billion years. The temperature drops through the threshold, and the field slides off zero. It does not switch on like a light. It settles. the way water settles into a lower basin, finding a new resting value, and staying there, because staying there costs less than returning, and everything immersed in it, which is everything, changes character in the same instant. Particles that were interchangeable stop being interchangeable. Some grip the field hard and become heavy. Some grip it lightly and stay nearly weightless. Some do not touch it at all and remain at light speed forever. For the first time in the history of the universe, it becomes possible for something to be at rest. That is the first instant of mass. Everything you have ever picked up traces back to a field settling into a new value in the first fraction of the first second, and to a symmetry breaking as it did. So the famous mechanism is real, it is confirmed, and it is essential. Without it, there would be no atoms, and therefore nothing at all. But the numbers it hands out are tiny, and we still have not accounted for the mass you can feel. Before we go looking for the rest, there is a correction to make about the most famous particle in modern physics, because almost everyone who has heard of it has been told the wrong thing. Nobody invented the Higgs field because they were curious about mass. They invented it because their mathematics had reached an impasse and would not move. In the early 1960s, physicists had a framework for describing forces that was beautiful and worked perfectly for one case. The framework is called gauge theory, and the case it worked perfectly for was electromagnetism. Quantum electrodynamics, that theory matching experiment to 10 decimal places, is a gauge theory. Naturally, people wanted to use the same mathematics on the weak nuclear force, the force responsible for certain kinds of radioactive decay, because a framework that good ought to generalize. It did not generalize, and it failed for a very specific reason. Gauge theories, in their simple form, only stay mathematically consistent if the particles that carry the force have no mass. The photon, which carries electromagnetism, is indeed massless, which is why the theory worked. But the particles that carry the weak force are not massless. They are enormous. The W boson weighs about 80 giga-electron-volts, and the Z boson about 91, which makes each of them somewhere in the region of 86 to 97 times heavier than an entire proton. Single elementary particles, with no internal structure, outweighing a proton nearly 100 times over. And if you simply wrote those masses into the equations by hand, the whole structure collapsed. The calculations began producing infinities that could not be removed by any legitimate procedure. The theory stopped predicting anything. You could not just declare that the W and Z bosons were heavy. The mathematics forbade it. What was needed was not a number, but a mechanism. Some way for those force carriers to acquire mass from inside the theory, generated by the equations themselves rather than inserted by hand, so that the gauge structure stayed intact and the infinities still cancelled. In 1964, 3 separate groups found the same answer within months of each other. Peter Higgs, working in Edinburgh, published a paper. François Englert and Robert Brout, working in Brussels, published a paper. Gerald Guralnik, Carl Hagen, and Tom Kibble, working in London, published a paper. None of them was collaborating with the others. All of them proposed essentially the same idea: add a new field to the theory, give it a non-zero value in its lowest energy state, let the force carriers interact with it, and mass appears on its own, generated by the interaction, with the mathematics still consistent and the infinities still cancelling. That is the Higgs mechanism. And it did not merely solve the W and Z problem. It solved mass for every elementary particle at once. Anything that interacted with the new field would acquire mass in proportion to the strength of the interaction. Anything that ignored the field would stay massless. The photon ignores it, which is why light still travels at light speed. Now, if the Higgs field is a quantum field, then it must have an excitation. Every field does. Ripple the electromagnetic field, and you get a photon. Ripple the Higgs field, and you should get a particle. That particle is the Higgs boson, and the theorists could predict that it existed while being completely unable to predict how heavy it would be, which meant the only way to settle the question was to build a machine powerful enough to make one and look. That took 48 years. The machine is the Large Hadron Collider at CERN, a ring 26.7 kilometers around, buried roughly 100 meters beneath farmland on the border between France and Switzerland, and part of its design brief was finding this particle. It works by accelerating protons to very nearly the speed of light in opposite directions and smashing them into each other, then sifting the wreckage. On the 4th of July 2012, in a packed auditorium at CERN, the spokespeople for the two big detector collaborations presented their results one after the other. Joe Incandela for CMS, Fabiola Gianotti for Atlas. Two separate detectors, two separate collaborations of thousands of people each, two entirely separate analysis chains, deliberately kept from comparing notes. Both of them had found the same excess in the same place, a new particle with a mass of about 125 giga-electron volts, both at the 5 sigma level, which in this field is the threshold for the word discovery and corresponds to a false alarm probability of roughly 1 in 3.5 million. At 20 minutes to 11 in the morning, the room applauded. Peter Higgs, sitting in the audience at the age of 83, listening to the confirmation of a paper he had written before most of the people in the room were born, wiped his eyes. The Director General, Rolf Hoyer, took the microphone and said, "As a layman, I would say, now we have it." Higgs and Englert received the Nobel Prize in Physics the following year. Robert Brout, who had written the Brussels paper alongside Englert, had died in 2011 and could not share it. He missed the confirmation of his own idea by 7 months. And now the correction, because this is where the public understanding of mass took a wrong turn that it has never recovered from. The Higgs boson does not give things mass. The discovery was reported worldwide under the nickname the God particle, which came from the title of a popular science book, and which Higgs himself disliked intensely, partly because he was an atheist and thought it might offend people of faith, and partly because it is scientifically misleading. The nickname left hundreds of millions of people with the impression that this particle is the source of mass in the universe, that mass is somehow made of Higgs bosons, and that the mystery was closed in 2012. Here is the actual relationship. The Higgs boson is an excitation of the Higgs field, in exactly the way a photon is an excitation of the electromagnetic field. To make one, you have to dump a very large amount of energy into a very small volume, which is what the collider does. And once made, it lasts for about 1.6 times 10 to the minus 22 seconds before it decays into other particles. That is a duration so short that a beam of light would cross less than the width of an atomic nucleus in the time available. You will never encounter one. Nothing in your body has ever contained one. They play no role in everyday physics whatsoever. Imagine you walk into a concert hall and hear a single note ringing in the air. That note tells you there is a piano somewhere in the building. But the note is not the piano. The note is a brief vibration the piano produced, and it will be gone in seconds, while the piano sits there whether anyone touches a key or not. The Higgs boson is the note. The Higgs field is the piano. There is a claim that circulates online that the discovery was overhyped, or worse, manufactured, to justify the cost of the machine. And it is worth answering directly rather than ignoring. The reason physicists are confident is not the announcement. It is the structure of the evidence. Two detectors, built to different designs, run by different collaborations, analyzing separately, found the same bump in the same place. And in the years since, the particle's behavior has been measured in detail. How often it decays into pairs of photons, into pairs of Z bosons, into bottom quarks, into tau particles. Each of those rates is a separate prediction of the theory, because each depends on how strongly the Higgs field couples to that particular kind of matter. If the mechanism were wrong, those rates would come out wrong. They have not come out wrong. The particle keeps behaving exactly as a field responsible for elementary mass would require it to behave, which is a much harder thing to fake than a single peak on a graph. It is also worth saying what the mechanism really is underneath, because framing it as mass creation slightly misses the point. Before the field settles, the equations describing elementary particles are symmetric in a specific respect. None of the particles has mass, and in that one respect, they are all identical. When the field takes its non-zero value, that symmetry breaks. The particles that couple to it become heavy, the particles that do not stay massless, and things that were interchangeable become distinguishable. The Higgs mechanism does not manufacture a substance. It destroys a symmetry, and diversity falls out of the wreckage. That is a different kind of explanation from the one most people are carrying around, and it is a better one. Detecting the boson proved the field is real, and that was the entire point of building the machine. But the field is what does the work. Silently, permanently, everywhere, including in the space your body occupies right now. The boson was the receipt. So the famous mechanism is confirmed, and the famous particle is real. And we are still, at this point, not much closer to the answer we came for. Because everything the Higgs field explains adds up to those 9 units inside a proton that weighs 938. Less than 1%. The most celebrated result in modern particle physics, the 48-year hunt, the packed auditorium, and the tears, and the Nobel Prize, accounts for under 1/100th of the weight in your hand. The other 99% is generated by something else entirely, something that got no headlines, no nickname, and no packed auditorium. And to understand it, we have to go back inside the proton and meet the strangest force in nature. Let us step back for a moment and put the pieces together, because we are about halfway through and the ground has shifted several times. We started with a sensation, the weight in your hand, and the entirely reasonable belief that it measures how much stuff is in there. We followed that belief inward, through elements and atoms and nuclei and nucleons, and at every level the arithmetic worked. Then we reached the quarks inside a proton, weighed them, and found they account for less than 1% of it. We learned that particles are not objects but excitations of fields that fill all of space. We learned that elementary particles get their rest mass from one particular field whose lowest energy state is not zero, and that this famous mechanism, the one with the Nobel Prize and the nickname, supplies exactly the 1% and none of the rest, which leaves an obvious and slightly uncomfortable position. The mass you can actually feel, the mass that makes a bowling ball hard to lift and a planet hold you down, has not been explained by anything we have discussed. It comes from the force that holds quarks together, and that force does not behave like any other force in nature. The theory describing it is called quantum chromodynamics, usually shortened to QCD. It is a quantum field theory, like the theory of electromagnetism, and structurally, the two look similar on the page. The name comes from the Greek word for color. Because the strong force operates through a property, physicists decided to call color charge. This has nothing to do with actual color. Quarks do not glow. Color charge is simply the label chosen for the strong force's equivalent of electric charge, and the choice was whimsical rather than descriptive. In electromagnetism, a particle can carry positive or negative electric charge, and the force is mediated by photons. In the strong force, a quark carries one of 3 types of color charge, named red, green, and blue, for no reason other than that 3 was the number required, and color mixing was a convenient mental image. Color-charged quarks attract and repel one another by exchanging gluons, in the same way electrically charged particles attract and repel by exchanging photons. So far this sounds like electromagnetism, with more labels. Then you notice the one difference that changes everything. A photon does not carry electric charge. It mediates the electromagnetic force between charged particles, but the photon itself is electrically neutral. It does not feel the force it transmits. Photons do not attract or repel each other. Two beams of light cross without noticing. Gluons carry color charge. The gluon is not neutral with respect to the force it carries. It feels its own force, which means gluons interact with each other. They pull on one another. They emit further gluons. They build chains and webs and tangled structures of their own. The messenger is also a participant, and once that is true, the whole character of the force changes. Here is what it changes into. Take two opposite electric charges and pull them apart. The force between them weakens with distance. The field lines spread out into the surrounding space, thinning as they go, and pull the charges far enough apart, and the attraction becomes negligible. That is why electromagnetism has long range, and why you can, in practice, separate a positive charge from a negative one whenever you like. The strong force does the opposite. When two quarks are very close together, the force between them is comparatively feeble. They rattle around almost freely inside a tiny region as though barely bound at all. Physicists call that asymptotic freedom, and it was discovered in 1973 by David Gross and Frank Wilczek at Princeton, and, independently and at the same time, by H. David Politzer at Harvard. It won them the Nobel Prize in Physics in 2004, and it was a genuinely shocking result at the time, because every force anyone had ever studied got stronger as things got closer, not weaker. Now pull those two quarks apart. The force does not fade. It holds, or it grows. The gluon field between them refuses to spread out the way an electric field does, because the gluons are pulling on each other and will not disperse. Instead, the field lines squeeze themselves into a narrow tube, a taut string of concentrated gluon energy stretching between the two separating quarks. And the further you pull, the more energy you pour into that tube, and the tube keeps taking it. It behaves like a rubber band. Stretch it, and it stores what you put in, and it resists harder the further you go. With a rubber band, eventually something snaps, and the tension is released. With the strong force, something snaps, and the result is stranger than release. When you have put enough energy into the gluon tube, the energy in the tube becomes sufficient to make new matter, and that is precisely what it does. The tube breaks, and at the break, a new quark and a new antiquark appear out of the field energy that was stored there. Each end of the broken string finds itself immediately paired with a fresh partner. So you started with two quarks and tried to isolate one. You ended with four quarks in two new pairs, and not a single one of them alone. Pull harder, and you get more particles, never fewer. There is no amount of effort that produces a lone quark, because the effort itself is what manufactures the company. This is confinement, and it deserves to be sat with rather than noted in passing. Quarks are permanently trapped inside composite particles. You cannot extract one and hold it up and look at it. This is not a limitation of instruments, and it is not a matter of waiting for a bigger accelerator. It appears to be a law. In the entire history of experimental physics, across tens of thousands of experiments at dozens of accelerators over more than half a century, no one has ever detected a free quark. Not once. There is no disputed candidate, no marginal signal that might be a quark if you squinted at the data, no result somebody is still arguing about. People have hunted them with dedicated searches, with oil drop experiments looking for fractional electric charge in matter, with cosmic ray detectors watching for the debris of collisions far more energetic than anything a laboratory can produce. Every result is a null result. Think about what an odd kind of law that is. Electromagnetism does not work this way. You can peel a negative charge away from a positive one and carry it across the room. Gravity does not work this way. You can separate two massive objects and move them as far apart as you please. But the strong force says no. You may not have a quark by itself. Attempt it, and the universe will convert your effort into new quarks, rather than permit a single violation. The force rewrites what is allowed to exist, rather than let one of its constituents stand alone. There is something almost stubborn about it, a relentlessness that operates at every energy anyone has ever tested, and it is the reason your hand is heavy. I should add one honest caveat, because it is the kind of detail that makes physics more interesting rather than less. Confinement has never been proved. It is supported overwhelmingly by experiment and reproduced convincingly in computer simulations, and essentially no physicist doubts it. But a rigorous mathematical demonstration that the equations of the strong force actually confine, starting from the equations and ending at the conclusion, does not exist. The problem has a formal name, the Yang-Mills existence and mass gap problem, and it sits on the Clay Mathematics Institute's list of Millennium Prize problems, with $1 million attached, unclaimed since the list was drawn up at the turn of the century. We use the theory daily. We build detectors around it. Nobody has proved it does the thing we watch it do. Because quarks cannot be alone, they always come in groups, and the bound objects they form are called hadrons. There are two main families. Baryons contain 3 quarks, and protons and neutrons are baryons. Mesons contain a quark and an antiquark, and pions and kaons are mesons. Hundreds of hadrons are known, all of them different arrangements of quarks held by gluons, all of them governed by the same theory. And now the connection to mass, which is the thing we came here for. The 3 valence quarks inside a proton are confined to a region roughly 1 femtometre across, which is 1/1,000,000th of 1/1000,000th of a metre. They cannot leave. The strong force will not let them, and the moment you try to help them leave, it makes more quarks instead, so they are stuck in a volume of almost incomprehensible smallness. Now bring in quantum mechanics, because a trapped particle is not a still particle. The Heisenberg uncertainty principle says that the more precisely a particle's position is pinned down, the less precisely its momentum can be defined, which in practice means that squeezing something into a small space forces it to move fast. This is not a metaphor or an approximation. It is why atoms have the size they do. Electrons cannot settle onto the nucleus, because confining them that tightly would demand more momentum than they can afford. Confine a quark inside 1 femtometre, and the momentum you force upon it is enormous. The valence quarks inside a proton are not drifting gently. They are moving at speeds close to the speed of light, ricocheting within a space so small that the word inside barely applies, changing direction constantly, unable to slow down and unable to leave. Energy of motion, at those speeds, is not a small quantity, and energy, as Einstein established more than a century ago, is not merely equivalent to mass in some loose accounting sense. It is mass. The two are the same property measured in different units, joined by a conversion factor that happens to be the speed of light squared, which means the answer we have been circling is starting to come into view. But to see it properly, and to see how much of it comes from the quarks and how much from something else, we need to go inside the proton and look at what is actually in there. And it is not 3 little balls in a bag. It is the most violent environment in the known universe, and there is one inside every atom of your body. Start with the size, because nothing else in this part will land properly without it. A proton's charge radius is about 0.84 femtometers, which makes the whole particle roughly 1 femtometre across. A femtometre is 1/1,000,000th of 1/1000,000th of a metre. Written out as a decimal, it is a naught, a point, 14 more noughts, and then a 1. About 100,000 protons laid side by side would just about span a single atom, and a single atom is already far below anything a light microscope can resolve. If an atom were a cathedral, the proton would be a pinhead somewhere near the middle of the nave. That is the container. Now let us go in. Imagine shrinking. Not gradually, not gently. You pass the scale of a cell, then the scale of a molecule, then the scale of an atom, and the atom turns out to be almost entirely nothing, an enormous quiet volume of electron cloud with something very small and very dense at its heart. You keep going. The nucleus resolves into individual nucleons, packed together, and you choose one and enter it. There are no walls. That is the first thing. You are inside a boundary that does not exist as a surface, only as the region beyond which nothing can go. 3 quarks are here with you, and they are not sitting in positions. They are screaming past at speeds close to the speed of light, reversing direction constantly, never settling, never slowing, ricocheting off nothing you can see. And between them, around them, through them, is something that fills the entire volume and moves faster than you can follow. Gluons, uncountable, splitting into pairs and merging back together, tugging on one another, building and dissolving structures continuously. The field is not a background here, it is the weather, and the weather is a storm with no calm anywhere in it. And then you notice the flickering. Pairs of particles appearing out of nothing, existing for a duration too short to be called a duration, and vanishing again. Quarks and antiquarks that were not here a moment ago and will not be here a moment from now, borrowed from the field and returned before anything can be measured. Some of them are heavier than the quarks that are supposed to be here. None of them belongs. All of them are constantly arriving. Nothing is still. Nothing is ever still. And there is no way out, in any direction, for anything. That is the interior of a proton, and now let us go through it slowly and account for what is actually there, because the details matter for the arithmetic. There are 3 valence quarks, 2 up and 1 down. These are the quarks that give the proton its identity, its electric charge, and its quantum properties. When we say a proton is made of 2 up quarks and a down quark, these are the 3 we mean. They are also, as we have established, responsible for less than 1% of its mass. Then there are the gluons, and this is where most people's mental picture is badly wrong. The gluons are not a thin connective tissue running between 3 dominant quarks. They are the majority population. When physicists probe a proton at high energy, they can measure how the particle's momentum is divided among its contents. And at typical probing energies, the gluons carry roughly half of the proton's total momentum. Half. They are not a detail of the binding. In terms of what is in there and how much of the action they account for, they are at least the equal of the quarks, and by number, they hugely outnumber them. And gluons are massless. This is worth stating flatly because of where it leads. A gluon has no rest mass at all. It takes nothing from the Higgs field. It is, in that respect, exactly like a photon, a massless carrier traveling at light speed. Half of the momentum inside a proton is carried by particles that weigh nothing. Then there is the sea. Mixed into the gluon storm are virtual quark and antiquark pairs, appearing and disappearing on timescales so short that individually they barely register. Physicists call them sea quarks, to distinguish them from the 3 valence quarks that define what the particle is. There are virtual up quarks and up antiquarks, virtual down quarks and down antiquarks. And more surprisingly, there are virtual strange quarks and strange antiquarks, particles roughly 20 times heavier than an up quark, which have no role whatsoever in the proton's identity, and which appear, anyway, briefly, as fluctuations in the gluon field. The proton contains particles that are not part of its definition, borrowed from the vacuum and given back. This is not speculation, incidentally. The presence of the sea and the gluon population is measured. It is what deep inelastic scattering data has been mapping for half a century, and the distributions have names and are catalogued. and are used to predict collision outcomes at CERN every day. It is also worth admitting how much about the proton remains unsettled, because the confidence of the next few minutes should be earned rather than assumed. For about a decade, this particle was at the center of a genuine measurement crisis known as the proton radius puzzle. Measurements made using hydrogen atoms, in which the electron had been replaced by a muon, a heavier cousin of the electron that orbits much closer in, gave a proton charge radius about 4% smaller than the value that ordinary electron-based measurements had produced. 4% does not sound dramatic until you see that both sets of measurements were precise enough that 4% was many standard deviations of disagreement. Later experiments have largely come down on the side of the smaller radius, but the episode is a reminder that we are describing an object whose size was in serious dispute within the last 15 years. There is a second unresolved puzzle inside the proton, and it is the mass puzzle's sibling. A proton has spin, and the obvious expectation is that its spin is the sum of the spins of the three quarks. It is not. Measurements show that quark spins account for only about a third of the proton's total spin, and the rest has to come from the spin of the gluons and from the orbital motion of everything inside. So the proton's spin, like its mass, is mostly not supplied by the things it is supposedly made of. Twice over, the same lesson. The properties of this particle emerge from what is happening inside it, rather than from an inventory of its parts. So if you could freeze a proton at a single instant and take inventory, you would not find three particles. You would find three valence quarks, dozens of gluons, and several transient quark-antiquark pairs, all packed into that same 1 femtometre, all moving at speeds close to the speed of light, all interacting furiously and continuously. It is one of the most energetic environments in the known universe, and it is compressed into one of the smallest volumes the universe permits. There is a further subtlety about that flickering, and it is a general feature of quantum field theory, rather than something peculiar to protons. Even in genuinely empty space, quantum fields do not sit perfectly still at their lowest value. They fluctuate. Virtual particles appear and vanish constantly, borrowing energy for intervals short enough that the borrowing cannot be detected. This is not a fringe interpretation, it is measured. The Casimir effect, in which two uncharged metal plates placed extremely close together are pushed toward one another by the vacuum around them, is a laboratory-verified consequence of it. Inside a proton, those fluctuations are far more intense than in empty space, because the gluon field there is so strong. The vacuum inside a proton is the least empty vacuum in nature. Now put the picture together with what we established about confinement, because the two halves lock into each other. The quarks cannot leave, the strong force will not permit it, and any attempt to help them leave manufactures more quarks instead. So they are confined inside 1 femtometre. Quantum mechanics then insists that anything confined that tightly must carry enormous momentum, which means enormous speed, which means enormous kinetic energy. That energy is not going anywhere either, because the thing carrying it cannot escape. And the gluon field is carrying its own energy, a great deal of it, stored in the tangled self-interacting structure that keeps the whole arrangement from flying apart. That energy also cannot leave, because the field is bound to the quarks, and the quarks are bound to each other. So what you have inside a proton is an enormous quantity of energy in several forms, trapped in a volume so small that the human mind has no reference for it, held there permanently by a force that would rather create new matter than allow a single escape. And energy has mass. Not in a metaphorical sense, not approximately, exactly. This is the content of the most famous equation in science, and it is usually taught in one direction only, as the recipe by which a small amount of mass can be converted into a very large amount of energy in a reactor or a bomb. That direction is real, but the equation is a statement of equivalence, and equivalence runs both ways. Energy is mass. Any system that contains energy behaves, in every measurable respect, as though it has the corresponding mass. It resists acceleration by that amount. It gravitates by that amount. It weighs that much. If you fill a sealed box with light, the box weighs more than the same box empty, because the light inside carries energy. The effect is far too small to detect with any light you could produce in a laboratory. But the principle is not approximate, and it is not up for debate. The energy in the box has mass, because energy and mass are one property. Inside the proton, that principle is not a curiosity operating at the 10th decimal place. It is doing, essentially, all of the work. The kinetic energy of quarks moving at near light speed, and the field energy of the gluons holding them, and the churning of the fluctuating vacuum between them, all of it contributes real, measurable, weighable mass to the particle. The quarks contribute 9 units of rest mass, and the proton weighs 938. We are now in a position to find the other 929 and to say where each piece of it comes from, because physicists have actually done the accounting. The numbers are specific. They were extracted from the equations of the strong force by brute computational force, and they will tell you, with real percentages, what you are made of. In 2018, a group of physicists published a paper in Physical Review Letters that did something people had been talking about loosely for decades, and nobody had pinned down properly. They took the proton's mass and broke it into pieces, not conceptually, numerically. They calculated, from the equations of the strong force, how much of the proton's mass comes from each distinguishable source, with error bars on every term. Here is the answer, and I want to walk through it slowly, because each line is a different kind of thing. The kinetic and potential energy of the quarks accounts for about 33% of the proton's mass. That is the energy of those 3 valence quarks tearing around inside 1 femtometre at close to the speed of light, plus the energy of their interaction. A third of the weight in your hand is the energy of motion of particles that cannot stop moving. The energy of the gluon field accounts for about 37%. That is the largest single term. More of the proton's mass comes from the field holding it together than from anything else, and gluons, remember, have no rest mass at all. 37% of the mass of ordinary matter is supplied by particles that weigh nothing. Then there is a term called the trace anomaly, and it accounts for about 23%. This one has no everyday picture behind it, and I am not going to invent one, because the honest description is that it is a purely quantum effect with no classical analogue. In the classical version of the strong force, there is a symmetry relating physics at different scales, so that shrinking everything and increasing all the energies proportionally would leave the theory unchanged. Quantum mechanics breaks that symmetry, because the strength of the strong force itself changes depending on the scale at which you look at it. The breaking of that scale symmetry contributes real mass to the proton. Nearly a quarter of what you weigh comes from the fact that the strong force does not look the same at every magnification. And finally, there is the term traceable to the quark masses themselves, the Higgs-given rest masses, the famous mechanism, the Nobel Prize, the packed auditorium. It accounts for about 9% in this particular accounting scheme, and the reason that number looks larger than the 1% I quoted earlier is a technical one worth being straight about. This term includes an effect where the quark masses are amplified by the strong dynamics rather than simply added, so it is not the same quantity as the naked sum of the quark rest masses. The naked sum is still about 1%. Either way, the conclusion is identical, and it does not depend on the bookkeeping. The overwhelming majority of a proton's mass is not the rest mass of anything. That business about the force changing with scale is worth 1 extra minute, because it is the same fact that produced asymptotic freedom, and it is doing double duty here. The strength of the strong force is described by a number physicists call the coupling constant. And the word constant is a historical embarrassment, because it is not constant. It depends on the energy at which you measure it. At the energy scale of the Z boson, around 91 giga-electron-volts, the strong coupling is a manageable 0.118, which is why collisions at those energies can be calculated with ordinary techniques. Come down to the energy scale of the proton's own structure, and the coupling grows until it is no longer small at all. The force is weak when you look closely and strong when you step back, which is exactly backwards from every force in daily experience. And the mathematical machinery describing that variation is what generates the trace anomaly term. Almost a quarter of your mass exists because the strong force has a different strength depending on how hard you look at it. The neutron tells the same story with slightly different bookkeeping, and it is worth confirming that the result is not a peculiarity of one particle. A neutron contains one up quark and two down quarks, and since the down quark is the heavier of the two, the naked quark rest masses inside a neutron come to a little more than inside a proton, around 11 or 12 units instead of 9. The neutron's total mass is 939.56. So the fraction supplied by rest mass is still barely more than 1%. And everything else is the same storm doing the same work. Whatever this mechanism is, it is not a quirk, it is how composite matter weighs. I should flag the caveat that a careful physicist would insist on. This decomposition is scheme-dependent. Exactly how much of the mass you attribute to quark energy versus gluon energy shifts a little depending on the energy scale at which you define the terms, and the four numbers are constrained by a sum rule to add to 100%, so they are not four independent measurements. What is not scheme-dependent, what survives every reasonable choice anyone has proposed, is the headline: the quark rest masses account for roughly 1%, and more than 90% of the proton's mass arises purely from the dynamics of quarks and gluons, from motion, from field energy, from confinement, from things happening rather than things being present. So the answer to the question we have been carrying since the beginning is this: the other 99% is energy. Now let me turn that on you, because it is easy to hear this as a fact about protons and much harder to hear it as a fact about yourself. Protons and neutrons carry more than 99.9% of the mass of every atom in your body. Your electrons are so light that they contribute about 0.03% of an atom's mass. So whatever is true of a proton's mass is very nearly true of your mass, scaled up by an enormous factor. If you weigh 70 kilograms, then more than 69 of those kilograms are the energy of quarks moving and gluon fields churning inside your own protons and neutrons. Under 1 kilogram is the rest mass of anything at all, and most of that comes from the same Higgs field that was sitting at 0 in the first instant of the universe. You are, by mass, almost entirely motion, held in place by a force that will not let go. That is not a figure of speech, and it is not a philosophical flourish. It is the hardest, most quantitatively verified statement physics is currently able to make about what a person is. If you sat down and did the accounting on your own body, kilogram by kilogram, you would find that the substance you thought you were made of comes to less than 1%, and everything else is trapped energy. And notice that the phrase has flipped. Less than 1% arrived, a while ago, as a gap in the arithmetic, a hole in a theory, something missing. It comes back now as a description of you. Less than 1% of you is stuff. The rest is what stuff is doing. There is an important thing to say here about what this does and does not mean, because the fact gets misused in both directions. It does not mean mass is fake. Mass is entirely real. The proton's mass is measured to 10 decimal places. It resists acceleration exactly as any mass does. It bends space-time exactly as any mass does. If you drop something, it falls, and the falling does not care in the slightest that most of its mass is field energy rather than rest mass. A wave on the ocean is not an illusion because it is made of water rather than being a separate object. The wave is real. It carries energy. It can lift a boat or capsize one, and calling it a disturbance rather than a thing changes nothing about what it does to you. And it does not mean that mass is simply another word for energy either, which is the opposite oversimplification. That slogan gets repeated constantly, and it flattens a relationship that is more precise and more interesting than the slogan allows. A photon has energy and no rest mass. Two photons flying in opposite directions form a system that does have rest mass, even though neither photon individually has any, because the system has energy that cannot be removed by changing your point of view. Rest mass is the energy a system has in its own rest frame, and that is a specific, well-defined, frame-independent quantity. Total energy depends on who is looking. The two concepts are exactly related, and they are not the same concept, and physicists are careful about the difference for good reasons. There is one more thing worth noticing about the famous equation, which is that almost everybody meets it running in the wrong direction for this story. In a reactor, or a bomb, or in the core of a star, a small amount of rest mass is converted into a large amount of energy, and the conversion factor is so enormous that a tiny quantity of matter produces a shocking result. The sun turns roughly 4.25 million tons of mass into radiant energy every second, and it will do so for billions of years, while losing well under 1% of itself in total. That is the equation as it is usually taught: mass in, energy out. Inside a proton, it is running the other way, permanently, and it never finishes. There is no reaction, no event, no conversion taking place. Energy is simply present, confined, and being present, it has mass. Nothing needs to happen for that mass to exist, and nothing can stop it existing without releasing the energy which confinement forbids. The heaviness of ordinary matter is not the product of an event. It is a standing condition. What has actually happened here is subtler than either slogan. Mass has turned out not to be a substance and not to be a single thing. It is a property, a single number summarizing the total energy content of a system in its own rest frame, and the mechanisms feeding into that number are several and unrelated to one another. Which raises the question you should be asking by now, and it is the right question to be suspicious with. How could anyone possibly know any of this? You cannot open a proton, you cannot extract a gluon and weigh it, and if you tried to extract a quark, the attempt would manufacture new quarks instead. The interior of a proton cannot be photographed, sampled, or visited. Every number I have just given you is a claim about a place no instrument will ever enter. So the fact that we can state those percentages at all, with error bars, is either an extraordinary achievement or an extraordinary bluff. It is worth finding out which. The equations of quantum chromodynamics are known. They have been written down for 50 years, and they are not especially long. The problem is that nobody can solve them. That sounds like an admission of defeat, and it is really an admission about mathematics. In most of quantum field theory, calculations are done by a technique called perturbation theory, which works by treating the interaction as a small nudge to a simpler situation and then computing a series of increasingly small corrections. It is how quantum electrodynamics achieves those 10 decimal places. You calculate the leading behavior, then a small correction, then a smaller correction, and the series converges quickly enough that a handful of terms gives you an answer more precise than any experiment can test. That method depends entirely on the interaction being weak. In electromagnetism it is, the relevant coupling is about 1 part in 137, so each successive correction is roughly 100 times smaller than the one before, and the series collapses toward an answer. The strong force is called strong for a reason. At the energy scale where a proton's structure lives, the coupling is not small, and when the coupling is not small, the corrections do not shrink. Each term in the series is comparable to, or larger than, the one before it. The method does not become imprecise. It fails completely, producing gibberish rather than a slightly wrong answer. So to calculate the mass of a proton from the fundamental equations, physicists had to abandon the standard toolkit entirely and do something that sounds almost brutish. They put the universe on a grid. The technique is called lattice QCD. Instead of continuous space, you work with a finite set of points separated by small distances. Instead of continuous time, you work with discrete steps. Then you place the quark and gluon fields on that lattice and simulate them directly, letting them interact according to the actual laws of the strong force, exchanging gluons, fluctuating quantum mechanically, storing energy in the field. You put in the known quark masses and the known coupling and the rules, and then you let it run, and you extract the total energy of the system. Divide by the speed of light squared, and you have a mass. Nothing about that is easy. The lattice has to be fine enough that the spacing between points does not introduce serious error, and large enough that the edges of the simulated box do not distort the physics, and those two requirements pull in opposite directions, and both cost computer time. Then, because the physical answer corresponds to zero spacing and infinite volume, and the actual physical quark masses, and no simulation can be run at any of those directly, you have to run many simulations and extrapolate in 3 directions at once. A serious campaign consumes tens of millions of processor hours and can occupy some of the largest supercomputers in the world for months. In 2008, a group called the Budapest-Marseille-Wuppertal collaboration published the result that settled the question. It appeared in the journal Science, and what they had done was calculate the masses of the light hadrons, including the proton and the neutron, from first principles, with all 3 extrapolations controlled and the uncertainties honestly quantified for the first time. Picture the moment, because it is a strange kind of drama. There is no experiment. There is no beam, no detector, no target, no radiation. There is a machine room with a great deal of cooling and a great deal of noise, and there are numbers moving through it. Somewhere in there, on a grid of points representing a cube of space-time, a few femtometers across, quarks and gluons are exchanging energy according to the rules of a theory written down in the 1970s. The simulation has been running for months. The extrapolations are being closed one at a time, the spacing driven toward zero, the box driven toward infinite, the quark masses tuned to their physical values, and a number comes out the far end. The number is the mass of the proton. Nobody put it in. It was not fitted, not tuned, not adjusted to match. It emerged from the dynamics, and it agreed with the measured value. That is the quiet, enormous satisfaction of catching a theory telling the truth about something it was never designed to explain. And it was not one number. It was the proton, the neutron, and a spectrum of other hadrons, all from the same equations, with the same inputs, all landing where experiment says they land. There is an obvious objection to raise at this point, and it is the right one to raise. If you feed the quark masses into the simulation as inputs, and the simulation then produces the proton's mass, are you not simply getting out what you put in? Is this not circular? It is not, and the reason is the shape of the arithmetic we have been following all along. The quark masses that go in account for about 1% of the answer that comes out. You are not putting in a proton and receiving a proton. You are putting in 9 units and receiving 938, and the 929 you did not supply is generated by the dynamics of the simulation itself. Furthermore, The quark masses used as inputs are not fixed by the proton at all. They are pinned down by entirely different observables, other hadrons and other measurements, so the proton's mass is a genuine prediction rather than a rearranged assumption. If the theory were wrong, this is exactly where it would break, and it does not break. There is also a standard worth naming, because it recurs throughout this subject. 5 standard deviations, usually said as 5 sigma, is the threshold particle physicists use before they will call something a discovery, and it corresponds to a chance of roughly 1 in 3.5 million that the result is a statistical accident. 3 sigma gets called evidence and is treated with polite suspicion. Both the Higgs boson and the neutron being heavier than the proton were established at 5. This is what makes the percentages in the previous part more than storytelling. We are not inferring the interior of the proton from a metaphor. We are simulating it, and the simulation reproduces the one thing about the proton we can measure to 10 decimal places. Then, in 2015, largely the same group went after a harder target, and the result is my favorite number in this entire subject. They calculated the difference in mass between the neutron and the proton. That difference is small. The neutron weighs 939.57 and the proton 938.27, so the gap is 1.293 units, which is about 0.14% of either particle, and it is the outcome of a fight. The down quark is heavier than the up quark, and a neutron has 2 downs to the proton's 1, which pushes the neutron's mass up. Meanwhile, the proton is electrically charged and the neutron is not, and the electromagnetic self-energy of all that charge crowded into 1 femtometre pushes the proton's mass up. The two effects work against each other, and they very nearly cancel. What is left over, after the cancellation, is 1.293. To calculate that, you cannot use the strong force alone. You have to run quantum chromodynamics and quantum electrodynamics together on the same lattice, because the answer depends on both, and you have to get each side accurate enough that their near cancellation still leaves a meaningful residue. They managed it to an accuracy of 300 kilo electron volts, and established that the difference is greater than 0 at 5 standard deviations, which is to say they proved, from first principles, that the neutron is heavier than the proton. And now consider what rests on that. Because the neutron is heavier, a free neutron is unstable. Left alone outside a nucleus, it decays into a proton, an electron, and an antineutrino, with a half-life of about 10 minutes. Which means that in the early universe, as things cooled, free neutrons steadily converted into protons, and protons are stable, and a stable proton, with an electron bound to it, is a hydrogen atom. Now run it the other way. Suppose the difference had gone the other direction, and the proton had come out heavier than the neutron. Then protons would be the unstable ones. They would decay into neutrons. There would be no stable hydrogen. And with no hydrogen, there are no stars, because a star is a hydrogen fusion engine. With no stars, there is no carbon, no oxygen, no iron, no rocky planets, no chemistry, and nothing whatsoever capable of noticing the problem. The entire existence of the universe, as anything other than a thin haze, depends on 1 part in 700, going one way rather than the other, in the mass difference between 2 particles. And that 1 part in 700 is itself the leftover of a near cancellation between the mass difference of 2 quarks, handed out by the Higgs field, and the electromagnetic energy inside a particle 1 femtometre wide. The most consequential number in nature, the one that decides whether a universe can contain anything interesting, comes out of exactly the 2 mechanisms we have spent this whole video pulling apart, working against each other at a scale nothing will ever see. So we know. We can calculate the mass of ordinary matter from the fundamental equations, we can break it into its sources, and we can predict a mass difference so delicate that the existence of stars hangs on it. The picture is not a story. It is a computation that matched. Which means we can finally deal with the question the title asked, and it is not quite the question you might think. Because we now know where mass comes from. We have not yet said what it is. Before we can say what mass is, we should be precise about what mass does, because in physics, a property is defined by its consequences and not by its feel. Mass does exactly two things. Both of them are measurable, both of them are familiar, and the relationship between them is one of the strangest facts in all of science. The first thing mass does is resist acceleration. This is inertia. Push something, and it pushes back, not out of preference, but because that is what mass is. The more mass an object has, the harder it is to change its motion, in any direction, from any starting state. A bowling ball is harder to get moving than a tennis ball, and harder to stop once it is moving. A lorry is harder to swerve than a bicycle. This resistance is what Newton captured when he wrote that force equals mass times acceleration, and the equation says something quite specific. For a given push, the acceleration you get is inversely proportional to the mass. Shove a 1 kilogram object with 10 newtons, and it accelerates at 10 meters per second squared. Shove a 10 kilogram object with the same 10 newtons, and it accelerates at 10 times the mass, a tenth of the response. The second thing mass does is create and respond to gravity. Every object with mass attracts every other object with mass. The Earth has enough of it to hold you against the floor with a force you experience as your weight. The Sun has enough to hold the Earth in orbit at a distance of 150 million kilometers. A galaxy has enough to organize the motion of hundreds of billions of stars across 100,000 light-years. Those two things are what mass means operationally. If you want to know how much mass something has, you either measure how hard it is to accelerate, or you measure how strongly it pulls on other things gravitationally. And here is the strange part. Those two entirely different procedures always give exactly the same answer. There is no obvious reason why they should. Resisting a push and attracting distant objects are conceptually unrelated behaviors. You could easily imagine a universe in which they were governed by separate quantities, so that some substances were hard to shove but gravitationally faint, and others were easy to shove but pulled like anchors. Nothing in the logic of physics forbids it. In our universe it never happens, at any scale, for any material, to the limits of every measurement anyone has ever made. Galileo bumped into this without having the language for it. He observed that objects fall at the same rate regardless of their mass, and that observation only makes sense as a coincidence of two cancelling effects. A cannonball has more mass, so gravity pulls on it harder, but it also resists acceleration more, in exactly the same proportion, and the two effects cancel so precisely that the cannonball and the wooden ball hit the ground together. If the proportion were even slightly off, they would not. Einstein took that coincidence and refused to treat it as a coincidence. He called it the equivalence principle, and made it the foundation of general relativity, published in 1915. And the theory that came out describes gravity in an entirely different way from Newton. Mass and energy curve the geometry of space-time. Objects then follow the straightest available paths through that curved geometry, and what we experience as gravitational attraction is the shape of space-time steering things. Nothing pulls. The floor holds you up, because the geometry you are trying to travel through bends toward the center of the Earth. And now the crucial point for everything we have established, because general relativity settles a question you might otherwise worry about. General relativity does not care where mass comes from. It does not distinguish between rest mass and energy. It does not check whether the mass in front of it was handed out by the Higgs field or generated by gluons in a confined volume. It responds to total energy, full stop. Whatever energy a system contains, from whatever source, curves space-time in proportion. So the gluon field energy inside your protons gravitates exactly as rest mass would. The kinetic energy of confined quarks gravitates exactly as rest mass would. There is no second-class mass, no asterisk, no reduced rate for mass that turns out to be energy on closer inspection. The gravity that holds you to the ground, the gravity that keeps the moon in orbit, the gravity that bends starlight around a galaxy cluster is overwhelmingly generated by trapped energy rather than by the rest mass of anything, and it is not weakened in the slightest by that fact. When the Earth orbits the Sun, both bodies are participating with their total mass, and more than 99% of each body's mass is strong force energy inside nucleons. The solar system is held together, in the main, by the weight of confinement. It is worth separating two sensations that your hands treat as one, because they have completely different explanations. When you press on a table, it feels solid, and when you lift the table, it feels heavy. Those are not the same phenomenon. Solidity is electromagnetic. The outer electron clouds of the atoms in your fingertips refuse to overlap with the outer electron clouds of the atoms in the tabletop, partly through electrical repulsion and partly through a quantum rule forbidding identical particles from occupying the same state, and that refusal is what stops your hand passing through the wood. Heaviness is something else entirely. It is gluon field energy and quark motion inside nuclei, curving spacetime. The same object delivers both messages through the same hand in the same instant, and the two messages come from two different forces operating at two different scales. Nothing in the sensation tells you that. You have to be told. Earth, for the record, weighs about 5.97 times 10 to the 24 kilograms, essentially all of it in atomic nuclei, and essentially all of that in energy rather than in rest mass. The planet holding you down is, by weight, mostly motion. Which brings us to a distinction that is easy to blur and worth keeping sharp. There is mass as a measured quantity, and there is mass as a physical origin, and they are not the same kind of thing. When you stand on a scale, you get one number, 70 kilograms, say. That number is clean and singular, and it tells you both of the things mass does, how hard you are to accelerate, and how strongly you and the Earth pull on each other. As a measurement, it could not be simpler. Behind that single number is a mixture. A tiny part of it is the Higgs-given rest mass of your electrons. Another tiny part is the Higgs-given rest mass of your quarks. The overwhelming bulk is quark kinetic energy and gluon field energy, and the trace anomaly inside your nucleons. Then there are smaller corrections in both directions. The electromagnetic energy binding your electrons to their nuclei, the chemical energy in your molecular bonds, the thermal energy of everything jiggling at body temperature, all of which contribute mass, because all energy contributes mass. And there is a subtraction, which is the most counterintuitive term of the lot. Nuclear binding energy makes bound matter lighter than its parts. Take carbon, the element most of your dry mass is built from. A carbon-12 nucleus contains 6 protons and 6 neutrons. Add up 6 free protons and 6 free neutrons, and you get about 11,268 units. Weigh the actual nucleus, and you get about 11,175. 92 units are missing, roughly 7.7 per nucleon. Where did they go? They were released when the nucleus formed. Binding a nucleus together lowers the system's energy, and since energy is mass, lowering the energy lowers the mass. The nucleus weighs less than the sum of its pieces, and the difference is called the mass defect, and it is not a rounding error or a theoretical nicety. It is what powers every star in the sky. Fusion in the sun's core assembles light nuclei into heavier ones. The products weigh less than the ingredients, and the difference leaves as sunlight. The light falling on this planet is the mass that used to be there. So even at the nuclear level, mass fails to be additive. The interactions between the parts change the total. which means that the question people naturally ask, "What is mass made of?" has been the wrong question from the beginning. Try this instead. What is temperature made of? The question does not pass, and everyone can feel why. Temperature is not made of anything. It is not a substance, and it does not have ingredients. It is a property of a system that arises from the motion of the particles within it. You can measure it with great precision. You can feel it. It has enormous physical consequences, up to and including whether you survive the afternoon, and it is not a thing. Mass is like that. It is a property of particles and systems, arising from field interactions and from energy content, and it is not made of smaller stuff, which sounds deflationary until you notice that it makes mass more interesting rather than less, because a property with several unrelated mechanisms behind it is a richer object than a substance. And that would be a clean place to stop, if it were the whole truth. It is not, because everything we have accounted for tonight applies to ordinary matter, and ordinary matter is a minority shareholder in this universe. We should be honest about the edges of the answer before we give it, because the answer is genuinely good and it is also genuinely partial, and pretending otherwise would be the wrong way to end a video like this. Start with the neutrinos, which are the most embarrassing particles in the Standard Model. For decades they were assumed to be massless, and the original theory predicted exactly zero. Then, in the late 1990s and early 2000s, experiments proved otherwise, and they did it sideways. Neutrinos come in three types, and they change from one type into another as they travel, an effect called oscillation. The supercomputer detector in Japan found it happening in neutrinos produced in the atmosphere, and the Sudbury Neutrino Observatory in Canada found it happening in neutrinos arriving from the Sun. That work received the Nobel Prize in 2015. And oscillation is only possible if neutrinos have mass, so a mass had to be admitted into a theory that had predicted none. How much mass? Nobody knows. The best direct measurement is an upper limit rather than a value. The Katrin experiment in Germany measures the energies of electrons emitted when tritium decays, and in 2025 it reported that the effective electron-neutrino mass must be below 0.45 electron volts, from 259 days of data and roughly 36 million measured electrons. Compare that to the electron itself, at 511,000 electron volts. The neutrino is at least 1,000,000 times lighter than the lightest ordinary particle in your body, and it may be lighter still. The collaboration is aiming at a limit near 0.3, which would still be a limit rather than an answer. Nobody knows where that mass comes from either. It may come from the Higgs field with couplings so absurdly weak that they look like a mistake, or it may come from somewhere else entirely, and the leading alternative is called the seesaw mechanism. In that picture there exist extremely heavy partner particles, right-handed neutrinos, which nobody has ever detected, and the lightness of the neutrinos we can see is a consequence of the enormous heaviness of the partners we cannot. Push one end of a seesaw far down, and the other end goes far up. If that is right, then there is a third mass-generating mechanism operating in nature, alongside the Higgs field and QCD energy, and we have not directly observed it. Then there is dark matter, and dark matter is where the accounting gets uncomfortable. Observations of how galaxies rotate, how light bends around clusters, how galaxy clusters hold themselves together, and how structure formed in the early universe all point to the same conclusion from independent directions. About 85% of the matter in the universe is not ordinary matter. It is something that has mass, that gravitates, that shapes the motion of stars and bends the paths of photons, and that does not interact with light and has never been detected in a laboratory. So everything in this video, the Higgs field and the gluon storm and the lattice calculation that matched, accounts for the visible minority. Roughly 15% of the matter in the universe is the kind whose mass we can explain. For the other 85%, We can measure the mass with real precision. We can map where it sits, and we have no idea what mechanism gives it that mass, or whether either of tonight's mechanisms applies to it at all. There is a genuine possibility, taken seriously by some model builders, that dark matter is bound by a confining force of its own, a dark sector with something like its own version of quantum chromodynamics. If that turned out to be true, then most of the mass in the universe would be binding energy, for the same reason most of your mass is binding energy, and the story would generalize beautifully. It is also entirely possible that it is nothing of the kind. And then there is the third gap, which is the oldest and the most quietly annoying. The Higgs field explains how elementary particles get mass without explaining a single one of the values. Every coupling strength is measured and inserted by hand. The electron is light, and the top quark is heavy, and nothing in the theory says why the ratio is 338,000 rather than any other number. If there is a pattern behind those numbers, finding it would probably require physics beyond the standard model, and the searching has been going on for half a century without result. And there is a fourth gap, which is about the Higgs boson's own mass rather than anybody else's. Quantum corrections in the theory should drive that mass up toward the highest energy scale in physics, something like 16 orders of magnitude above the value actually measured, unless a set of very large contributions cancel one another to an almost absurd number of decimal places. Nobody knows what performs the cancellation. Supersymmetry was invented partly to do it, and has not shown up at the collider. Extra dimensions have been proposed, and have not shown up either. So the field that hands out mass to elementary particles has a mass of its own that the theory cannot account for, which is a peculiar situation to be in after 50 years. I should mention, in fairness, that some physicists prefer to solve the dark matter problem by changing gravity rather than adding matter. The best developed version of that idea is called modified Newtonian dynamics, and it does something impressive. It reproduces the rotation curves of a great many galaxies using a single new parameter, which is a better fit than a theory with no right to work at all should manage. It also struggles badly with galaxy clusters and with the detailed pattern in the cosmic microwave background, which is why most of the field still expects the answer to be a particle. But the question is open enough that honest people disagree about it. Sit with the shape of that for a moment, because it is a strange thing to be true at once. Physics can calculate the mass of the object in your hand from first principles, starting from the equations of the strong force and ending at a number that matches experiment, and physics cannot tell you why the electron weighs what it weighs. The confidence and the ignorance are printed on the same page, in the same theory, using the same symbols. 85% of the mass in this universe is unexplained, and we do not say that with frustration. We say it the way you would say, there is a room in the house nobody has opened. I should also address, briefly, what circulates in the gaps, because it does circulate, and it is better to meet it than ignore it. There is a proposal, associated with a small number of researchers, that inertia arises not from the Higgs field, or from confinement, but from interaction with the fluctuating electromagnetic vacuum. It has been published, it has been criticized on grounds of internal consistency, and crucially, it has never reproduced the observed spectrum of particle masses, which lattice QCD does. There are claims that mass is entirely electromagnetic in origin. Electromagnetic self-energy is real, and it appears in this story as one of the competing terms in the neutron-proton difference. But it cannot generate the hadron spectrum, and the calculations that can are the ones we walked through. And there is a much older idea, taken seriously by Einstein himself and explored quantitatively by Dennis Sciama, that inertia arises from the gravitational influence of all the distant matter in the universe. That is a genuinely interesting thought about the origin of inertial frames, rather than a working account of why a proton weighs 938, and general relativity, as actually formulated, does not implement it. What all of those have in common is that they are attempts to answer a question that has, for ordinary matter, already been answered, and answered with numbers. Which means it is time to answer the question this video started with, not where mass comes from, which we have now traced through 2 mechanisms, 4 contributions, and 1 supercomputer calculation, but what mass actually is. Here is the answer, plainly, and then we will sit with it. The true nature of mass, according to quantum physics, is that mass is not a substance, it is a property. It is a single number that summarizes the total energy contained in a system as measured in that system's own rest frame, and it arises from field interactions and from confined energy rather than from any quantity of material. For elementary particles, that property comes from coupling to a field whose lowest energy state is not zero. For composite particles, which is to say for everything you have ever touched, it comes overwhelmingly from the energy of motion and field dynamics trapped inside a volume too small to picture by a force that refuses to release its own constituents. At no level of description does mass turn out to be made of smaller, heavy things. At every level it turns out to be a consequence, and it is completely real. That is the part I want to protect from the mystics. It gravitates. It resists acceleration. It bends the geometry you walk through. It decides the structure of atoms, the stability of hydrogen, the burning of stars, and the arrangement of galaxies. Nothing about calling it a property, rather than a substance, makes it one particle less real. For thousands of years, mass looked like the one thing in nature that required no explanation. Things were heavy because they were made of stuff, and stuff was heavy because it was stuff, and the question closed itself. You could break an object into pieces, and each piece had mass. You could break the pieces into atoms, and each atom had mass. Mass was there at every level, solid and irreducible and unexplainable in the way that only genuinely fundamental things are unexplainable. It was not fundamental. It has mechanisms. It has origins. It has an explanation, and the explanation goes all the way down and finds no flaw made of substance, only fields and their excitations and the energy of their interactions. The universe is not built out of stuff. It is built out of fields, and mass is one of the things fields produce, not by being material, but by interacting, by confining energy, by breaking a symmetry, by doing what fields do. Which means the correction I made in the middle of this video was not really a technicality about one particle. It was the whole shape of the answer. The note is not the piano, and it is not just the Higgs boson that is a note. The electron in your fingertip is a note. The quarks in your bones are notes. Every particle you are built from is a brief structured disturbance in a field that fills all of space, and the fields are the instrument, and you are something the instrument is currently doing. So pick up the stone again. Feel the weight in your hand. It is unchanged. The same pressure on the same palm. The same small effort in the same wrist. The same information your body reads, without instruments and without thinking. Nothing about the sensation has moved, but look at what is underneath it now. Inside that stone, there are atoms, and the atoms are almost entirely empty, and nearly all of their mass is gathered into nuclei you would need to magnify a cathedral to a planet to see. Inside each of those nuclei there are protons and neutrons, and inside every single one of them there is a region 1 femtometre across, containing 3 quarks, moving at nearly the speed of light, because they cannot slow down and cannot leave, wrapped in a storm of gluons that weigh nothing at all and carry most of the mass, with quark-antiquark pairs flickering into existence and out of it faster than the word instant can be applied. Every one of those tiny storms is contributing its energy to the number your hand is reading. There are more of them in that stone than there are stars in the observable universe by an unimaginable margin, and all of them are raging, and none of them will ever stop, and the sum of all that fury is the reason your wrist is working. Less than 1% of what you are holding is stuff. The rest is what stuff is doing, and there is a thread running back from your hand to the beginning of everything, which I want to draw once before we finish. The reason those quarks have any rest mass at all is that a field slid off zero in the first 100 billionth of a second and has stayed off zero ever since. The reason they are confined into nucleons is a force whose messengers pull on each other, which is a property of one term in one equation. The reason the nucleons are stable enough to build a stone is that the neutron came out heavier than the proton by 14/100%. A residue left over after two effects nearly cancelled. Change any of those three, and there is no stone, no hand, and nobody to lift it. The weight you are feeling is not an incidental property of matter. It is the accumulated consequence of three decisions the universe made in its first instant, and it has been sitting in your palm all along, unremarkable, waiting for someone to ask. It also settles the question we kept circling, about what kind of answer this is. Mass turns out to belong to the same family as temperature, real, measurable, consequential, and not made of anything. Nobody finds temperature disappointing for being a property rather than a substance. We only expected mass to be different because we can feel it so directly, and directness is not the same as depth. The most immediate sensation available to a human body turns out to be reporting on the least intuitive physics in nature, and reporting it accurately, and reporting it every time you lift anything at all. There is something humbling about arriving here, and something oddly moving about how we arrived. Human beings living on one small planet, using nothing but careful thought, patient measurement, and a series of increasingly clever experiments, took the most ordinary sensation available to them, and refused to accept that it needed no explanation. They asked why things are heavy. They followed the question down through atoms and nuclei and nucleons and quarks, through a field that fills all of space and a force that will not let go, and they arrived at an answer nobody would have guessed at the start, and then they checked it, and it held. And the story is not finished, which is the best thing about it. We still cannot say why the electron weighs what it weighs. We still cannot say what gives dark matter its mass, and dark matter is most of the mass there is. There may be a third mechanism hiding in the neutrinos. Those questions are open tonight, and they are being worked on tonight, by people who will hand them on again if they have to. But what we already know is remarkable enough to change an ordinary gesture. When you hold something heavy, you are holding trapped energy. You are feeling the consequence of quantum fields interacting inside spaces smaller than a trillionth of a millimeter, held there by the strongest force in nature, and you are feeling it directly, with your hand, right now, without any apparatus at all. The quantum world is not a distant abstraction, available only to people with particle accelerators. It is the weight of a mug. It is the resistance of a door. It is the effort of standing up. Mass is not what you thought it was. It is not the amount of material in an object. It is the energy of fields and the consequence of their interactions, measured as a single number, felt as a single sensation, and arising from processes so intricate that working them out took the best minds available to our species more than a century of patient effort. It is something stranger and better and more beautiful than substance could ever have been. Thank you for spending this time with me inside the proton. If you found this kind of slow walk through physics worthwhile, a like or subscribe would mean a great deal, and it genuinely helps me keep making these. And remember, the next time you pick something up and feel how heavy it is, almost none of what you are holding is stuff. Good night, and may you never look at the weight in your hand the same way again.